that today we have a different kind of after-class activity. So there's a question on the CS 102 dev site called list practice. So that one is due by Thursday at 9:30. So that's just to get you some practice using lists. It shouldn't take you too long to write that program. So we'll have you, just want to let you know because that one is not showing up on Canvas. Okay, so that's one you need to make a mental note of or just jot down right now. But it's due on Thursday, 9:30 a.m. Okay, so today we're going to continue our discussion of lists. And if you remember, the list class is part of the C++ standard template library, and we include it in our programs using include list. And when we declare a list, we have to tell C++ the type of value it stores by putting it in angled brackets just like we would a vector. And a list is just like the list that we keep ourselves. So it could be a grocery list or a list of tasks. And I showed you last time how it's implemented using pointers, but don't worry about that for the time being because we'll get to that in another couple weeks. If you want to iterate through the list, then in fact it actually is worth showing you the conceptual, what the list conceptually looks like. So conceptually, the list in the STL has what we call a sentinel node at the beginning, then some number of elements, and then at the very end, another sentinel node. And the list is doubly linked in the STL, so you can traverse it either forwards or backwards. So to iterate through it, you use something called a list iterator. And that, if I name my list iterator LIT, then that always points to the current element of the list. And as we'll see, I can have more than one iterator at a time, and they can point to different list elements. And we can go forward with our list iteration, and if you remember, lines.begin gives you an iterator that points to the first element of the list, but lines.end gives you an iterator that points to sentinel node. Very good. So it does not actually give you a iterator that points to the last element of the list. It actually gives you an iterator that points to the sentinel node. Okay, and that way you actually will go through all the elements of the list before hitting the sentinel node and exiting. And then we showed you that there is a reverse iterator that you get using rbegin, and rend returns the sentinel node at the beginning of the list. And even with a reverse iterator, we use plus plus. Even though we're going in reverse, plus plus advances it to the previous item. If we use minus minus, it backs up the iterator to the previous element in whichever direction we're going. And to get at the value of the list node to which the iterator points, we dereference it using the asterisk, so that will return the value of the list element to which the iterator points. And finally, to declare an iterator, you have to tell it the type of list it is going to be iterating over, including the type of value. And then you see the colon colon, and then either iterator or reverse iterator. The final thing we talked about was how you insert into a list using the insert command, and you give the insert command 2 arguments. The first is a iterator that points to the node that you want to insert before or after. Let's take a vote. How many of you think that insert is going to insert before the iterator, before the item? Okay? And how many think it's going to insert after? Okay? For those of you, all right, I appreciate that. I'm with you, even when we're wrong. So it is before. It inserts before the item pointed to. So in this case, we'd actually be inserting at the front of the list. Okay, and the second element, or the second argument, is the value you're inserting. So the STL list, the insert function, it will create the list node, put the value that contained in S, it will copy that value into that list node, and then it will insert that list node before that iterator. So that's where we left off, okay, with inserting into the middle of the list. So today we pick up with how we delete items from the middle of a list. Then we'll talk about why using a list in this situation where we want to insert in the middle or the beginning is better than using a vector. Then we'll talk about a third form. So we have vectors lists. We'll talk about a third data structure, doubly ended queues. We'll give you a quick diversion back to vectors and how you can sort a vector. And finally, we'll give you a list example at the end. So if we want to delete items from the middle of the list, an obvious example is you scratch off a grocery item from the middle of a list as you're going through the grocery store. I'll give you another example, which is, let's say we want to sort the elements on a list. So we want to produce them in sorted order. So for example, let's say our list contains the elements 8, 2, 1, and 10, and we want to output them in sorted order. Well, one way we can do that is we can search the list for the smallest item, delete the item from the list, and print it. So if we do that, we find 1 is the smallest item, so we output 1, and when we delete it from the list, we're left with 8, 2, and 10. So again, we search for the smallest item, which is 2. We print it and delete it from the list, and notice it's being deleted from the middle of the list, so we're left with 8 and 10. Now we find that 8 is the smallest item and output it, leaving us with 10. Finally, 10 is the only item left, so we output it, and now the list is empty. So very simple sort function, not particularly efficient. You'll see more efficient sort functions when you get to CS302, but this one works, and it does delete from the middle of the list. So I put the code for it in sort.cpp so you can have a look. But the part we're interested in is the part where the sort function essentially calls a function called findMin that's going to find the minimum item in the list and is going to delete it and return it. So you notice we have to pass it by reference because even we are modifying it, so we actually do need to pass it by reference, but even if we were not modifying it, we would pass it by reference because it's a big object and we don't want to copy it. So to find the minimum value, this is going to be an example of using 2 iterators. So I start, and I always initialize min to the first item in my list. Okay, that's a perfectly good place to start. And then I have my other iterator iterating through the list. So essentially, min is always keeping track of the minimum item I've seen so far, so that when I am out of the loop, min will point to the smallest item in the list, and lit is going through each item in the list. And each time I move to a new item, I compare my two values, and if the list item I'm currently at is less than min, then I set min to be equal to this new lit item. And when I'm done with my list, min points to the minimum element. Now, I save the return value and then erase. So this is the first time you've seen the delete command. So erase is the delete command. Why they didn't use delete, I don't know. They used erase. So the idea of like an eraser. And it deletes that item pointed to by the iterator. So you give the erase method a iterator that points to the item you want to delete. It deletes it, and now we return the return value. Okay, I got a question for you. Why did I have to save the return value? I mean, why couldn't I just, let's see here. For some reason, this version of Chrome isn't, shoot. Okay. I had to reset Chrome over the weekend, and it lost the plugin I had for doing inking. So I won't bring that down now, but I will ask you, why couldn't I just say boxes.size erase min and then return star min? Because there's nothing in min now. It's been deleted. So I have to save the value of min because once I erase it, it's gone. Okay. So that is the sort function. In fact, if we look at sort for just one moment, the one interesting thing, you haven't seen this method. So it says while not lines.empty. So the way we check to see if a list is empty is with the empty method. And you can see it's a very simple sort procedure, 2 lines. While not lines.empty, print whatever find min returns. So, questions about deleting from the middle of the list. This was our little example with deleting from the middle of a list. We good with that? Okay. So I got the question last time from you. Why do we use a list rather than a vector? And my answer was, anytime we want to insert anywhere other than at the end of a vector or delete anywhere than at the end of a vector, we should prefer a list to a vector. And let's look at the reason. So first of all, you can insert into a vector if you don't have push front. Fortunately, C++ did not go so far as to give you a push front method. But I could simply change the list to a vector, and I can use exactly the same code to insert into a vector at the beginning. Okay, so I can get an iterator to the beginning of the list, just like I can with a list. So this code works, and it reverses the list. But here's the issue. In a vector, I have a vector, and right now that vector has these elements in it. Let's say 3, 8, 5, 6, 2, 1. Let's say I want to insert a new element at the front. I want to insert 10. Well, in order to put 10 at the beginning, I can't just add a new entry here. That doesn't work. Okay, it's just not the way things are implemented internally. The only way I can insert into the vector is if I create room at that first element by moving, whoops, that's not what I wanted, is I have to move every single element. I have to add a new element at the end. and then I have to move every item one element to the right. That's not too good. Every element has to be moved one to the right. You can see that in an array or vector of size n, that means I have to move n items. Just to insert one new item at the front. Whereas in a list, I don't have to do any such moving. I just add another item to the front and make it point to the previous front item. It's a lot easier. Okay, so that's just one insert. So one insert equals move n items. So if I do n inserts, that's essentially equal to move n times n, or n squared items. That's not too good. Okay, if I want to insert, say, 10,000 items, then I'm going to have to move 10,000 times 10,000, which is 10 to the 8th power, which is, I believe, 100 billion. I don't care how fast the computer is, moving 100 billion items is going to take a lot of time versus moving 10,000 or inserting 10,000 items in a list. Okay, so Dr. Planck actually programmed it up. So first of all, he said this is what the insert is equivalent to. It's equivalent to resizing the vector, and then for every item in the vector starting at the right-hand side, just like you did with the PGM labs, you had to move the rightmost item one item to the left. This is what this statement does. It moves the rightmost item one item to the left. And finally, at the end, you've created a hole at the 0th entry to insert X. Okay, so Dr. Planck coded up both of these. Both of these were reverse functions where we were inserting at the beginning of the list, and then when we traversed the list, it reversed the elements. So it printed them out in reverse order. So what he did then was he tried to reverse a 10,000 element list, and then he tried to reverse a 40,000 element list. And reverse 3 is the list implementation, and you can see you can use the time command to time how fast things go. So in this one, it took about, the U is the amount of user time, the S over here is the amount of system time, and this is the wall clock time. So what we care about is the amount of CPU time used by the user. So for a list, you can see that it went from, it was just 1/100th of a second, it went up to 2/100ths of a second. But when, I'm sorry, yes. But when we use the vector implementation, wow, it's 45 times slower on a 10,000 element list. And it is now, this was 7 seconds versus 0.02 seconds. 350 times slower on a 40,000 element list is our vector. Okay? And if you think about it, 40,000 squared is 16 times bigger than 10,000 squared. And sure enough, if we multiply 0.45 by 16, we come up with roughly 7. Dr. Planck didn't even bother with a 100,000 item list because he could have gone off to lunch, even on today's super fast computers, gotten lunch, and then come back, and maybe it would have been done. So the point is, vectors are really bad if you try to insert into the middle of them or delete from the middle of them. They just move like a snail compared with a list. So Did that kind of answer your question? I know I hit a dead horse with it, but beating a dead horse, but there you go. And if you're wondering about this little thing, /dev/null, that's a cute Unix trick. So that sends your output, that basically, instead of printing your output on the console or printing it to a file, it sends it to the proverbial bit bucket or trash can. So it actually ends up not writing it out, and you don't waste the overhead associated with writing something. It just goes to /dev stands for the device directory, null stands for printing to a null device. So you'll sometimes hear Unix programmers talk about /dev/null, and like your comment went to /dev/null. It's a Unix programmer's way of putting you down, saying it went in one ear and out the other. Okay, so that's what /dev/null means. Okay, so we don't want to use a vector unless we are inserting to the back of the vector and deleting at the back of a vector. But there is a common situation where we'd like to delete from the front of a line or list and add to the back of it. Can anyone think of that common situation of removing something from the front of a list, adding things to the back of a list?
Like a horizontal flip.
So like a horizontal flip, you're right. I was actually in real life. We do this all the time. We sit in line. So I was just looking for a real world. So we sit in line. If I'm at the cashier takes the first person from the line, from the front of the line, and we come into the back of the line. Okay? So that's a queue. Mathematicians, what can we say? They didn't use line, they used queue. So it's a queue, and we would like to be able to implement that kind of queue efficiently because they come up all the time. Like when you submit print jobs, those go into what's called a print queue. And the printer removes the first one from the queue and prints it. And when your job goes to the print queue, it goes in at the back. So queues are used a lot. Operating systems use them all the time for scheduling. So C++ has a DQ for doubly ended queue. So you include it with the doubly ended queue. And again, you declare it and tell it the type of value it is storing. And DQs are optimized to insert either at the front or the back and to delete at either the front or the back. So here's our reverse example again. It's the same as before. We just replaced a list with a DQ. Notice with a DQ, I am allowed to use, what am I allowed to use with a DQ? What's it look like? If it walks like and quacks like? Looks like a vector because we are using subscripts. Again, we're using indices. So in fact, DQs use very clever implementations of vectors. They use what are called circular vectors, and we're not going to talk about them in this class. They're a little beyond the scope of this class. But they're doing something very clever with vectors, and by doing something very, very clever with vectors, they're able to actually get very fast performance where they can remove or insert items at either the front or the back efficiently. But they still can't insert or delete from the middle efficiently because they actually are implemented using vectors. They're still no good for doing inserts or deletes in the middle. So you only use these DQs in situations where you are inserting at the front and the back and deleting at the front and the back, i.e. every time you need to simulate a line. Okay, so DQs, I'll even write it down because it's that important. DQs are good for simulating or for implementing, not simulating, for implementing lines. Because lines are first in, first out. You'll often hear them referred to as also FIFO queues, because mathematicians just love to use jargon, and so do CS types. This stands for first in, first out. Which is what it is. First person in line is the first person out. Okay, and Dr. Planck runs that version of reverse, and you can see it is blazingly fast. It is for 10,000 items, 0.004, and for 40,000 items, it's 0.03. If we go back and look at how long it took the list, it's at least competitive, 0.03 versus 0.024. In fact, DQs in practice tend to be faster than lists when you're doing inserts at the front or the back. So here's another example from Dr. Planck. So you actually get two examples, not just one. I said we'd look at two list examples. Here's another one where we're doing the tail function, where we want to print the last n lines of a file. In this case, he's hard coding the last 10 lines of the file. So he's going to start with a list implementation. And you can see at any time, he's only going to keep 10 lines on the list. So he gets his line, he pushes it back, so he's essentially keeping the lines of the file on a list. But if the size, so here's the size function, if the size of the line becomes greater than 10, he erases the first item of the list. Hence, he always is only storing 10 items in his list. And now he prints it out at the end. He prints out the 10 items. Very short and sweet. And by changing this list to either a vector or a DQ, he can run exactly the same code without changing anything else. He can change the two lists to vector or DQ, and change the include. And he can use the same thing for a vector or a DQ. So he does that. And again, he codes everything up. And he times them. They're not really that much different. You can see that with a list, it is 0.4 of a second. With a DQ, it's just slightly faster. With a vector, it's just slightly slower. So that was 10 items. But then he did it with 100 lines. Okay? And he didn't put it in here, but we're going to do it for grins. So we will go to CS140, notes lists, and he did it now. So these three, big my tail with a DQ list and vector, these now do 100. They print the last 100 items. So we will run time with big my tail DQ. And it didn't find it because I have to put that in front of it. Okay, so on a DQ with a 100 item tail, it's 0.4 seconds. Now we're going to run it with a list. It's 0.67 seconds. So it wasn't as good as a DQ, and now we run it with a vector. This is all with 100. Now they're starting to spread out. Now the DQ is 2 times as fast as the vector and is at least half as fast as the list. So the DQ is actually starting to beat the list. That's my point, is that DQs actually are faster than lists when you insert or delete only at the front or back. So at the very end of his notes, Dr. Planck has a little summary. So this is the summary. If you're simply accessing n items in order, or you are always adding to the back or deleting from the back of a list, use a vector. If in addition you want to insert at the front or delete from the front, use a DQ. If you want to insert and delete elements in the middle of the data structure, use a list. So this is your rule of thumb. We're giving you more tools. So when you are thinking about efficiency, this is how you choose between these three items. On midterm 2, I will give you scenarios, and I will ask you to select the best data structure to use. So you should be memorizing these kinds of rules because they are incredibly important. Okay, so these were not at the bottom of his notes because there's some material he doesn't go over, but they're near the bottom of his notes, right after Diamond Hunt. Yes?
In the reading, we also learned queues. Is there a time where we would use a queue over a DQ?
So a DQ implements a queue. Okay? A queue is a, going back here, when I said DQs are good for implementing lines, I was trying to come up with the everyday usage of it. Here's the computer science word for lines, queues. So in fact, you use a DQ to implement a queue. Okay? So a queue is actually a first in, first out item. I think we also covered stacks in the reading, right? Am I mistaken in that? We did not cover stacks. Okay. Then I will not burden you with that just yet. Okay. So let's actually take one more look at a list. So Dr. Planck loves topcoder. To give you an idea of how much Dr. Planck likes coding, Dr. Planck, when he takes a break, likes to turn to a good topcoder problem to challenge himself and code it up. So we might play games or go off and chew the fat over the with a cup of coffee. Dr. Planck goes to topcoder and he finds a topcoder problem to solve. So here was Diamond Hunt. So Diamond Hunt is one where you are given a so-called mine. And we're mining for diamonds. And the way it's implemented is actually as a string with either greater than or less than symbols. And every time we get a less than and a greater than symbol together, that's a diamond. And what we want to do is count the number of diamonds in the string, hence the term Diamond Hunt. So you're looking at this and you're saying, whoa, wait a minute, there's not 3 diamonds in there. I only see 2 diamonds. What gives? Well, what gives is that every time we find a diamond, we delete it. So when we delete these 2 diamonds, yes, oh, there is a, when we delete those 2 diamonds, we end up with a left and a right next to each other, which gives us diamond number 3. Okay, so by mining, wouldn't this be great if we could actually mine for diamonds, and as we remove exhaust diamonds, we create more diamonds? So this actually has 3 diamonds. This one has no diamonds. This one has 9 diamonds. So you delete the first diamond, and now those become a diamond. Delete those and these become a diamond. So they give you some examples like they always do in Topcoder. So whenever you delete a diamond, you may create more diamonds. Are we good with that? Okay. So there is a straightforward way to do this using the find and the substring commands. So we'll do that first because it's a fine example of showing you how to do this with the string functions. So you are getting a class diamond hunt. You're implementing the method count diamonds. You get this string, which we call a mine because we're mining it for diamonds. So we're going to start by using ND for number of diamonds, and we go into an infinite loop. And Dr. Planck is old school, so he uses 1 rather than true. So we use the find function to see if there is a diamond. We find the first diamond using the find function. If there is no diamond, then the find function returns string : NPOS for no position. There is no diamond. So at that point we return. That's why we're really not in an infinite loop, because eventually there will be no more diamonds. We really will exhaust the mine. And at that point we return the number of diamonds. But if we find a diamond, we increment ND++, and now we need to remove that diamond from the string. And the way we do that is with the substring function. So we went every part of the string that precedes, so this part gives us the part of the string that precedes the diamond. So 0 to I gives us what precedes the diamond, because I is the number of characters we want. And then this starts after the diamond and gives us everything after the diamond. Okay, so basically when we find a diamond, the first one gave us everything before the diamond. The second one gives us everything after the diamond. Okay, good with that? I'm sorry, in fact, let me use the board just for a moment because I think it does help to just see what's going on, but not with that green pen. Actually, I don't need the board. Here, let's do it with, okay, let's just copy this into here. Okay, so what we're doing is we have, initially we have, whoops, greater than, less than, greater, less than, greater than, this, and less than. So when we find the first diamond, it's right here. So what the first substring does is it returns this part of the string, and the second one returns that part of the string, and they put them together, and what we end up with is this getting deleted. So in fact, I'll just erase it. Okay, and we're left with that. Okay, so the next find is going to find this one. Okay, so now again, the substring function is going to find, the first one will return this one, the second substring returns that one, and when we put them together, we lose that, right? And so we're just continuing along merrily like that. So that's what these two are doing. It's concatenating the front of the string with the end of the string. Okay, so it's very nice, simple code. And we test it out, and it turns out to work just fine with our different strings. So he enters each of the strings. But again, he says, okay, it's nice, it's elegant. Think about the running time. Is this really good from a running time perspective? And the answer is no, it's not. In particular, think about the worst case kind of string. Okay, it's going to have to search through half of the string to find the first diamond. Okay, and that's essentially n divided by 2 characters. Now it deletes them. Well, the second time through, it again is having to go to the middle of the list. It's again looking at roughly n divided by 2 characters. So each time through the string, in the worst case, it has to look at n divided by 2 characters, and there may be up to roughly n divided by 2 diamonds. So in this case, I think there's something like 17 or 18. I think there's 18 characters, and there was 9 diamonds. So if you are doing, if there's roughly n divided by 2 characters each time, so you look at n divided by 2 characters, and there's n divided by 2 diamonds, that's n squared over 4. That's just the find. But there's more. The substring also has to do something. The substring is in effect looking at the entire string. So unlike this is just find, the substring is worse. The substring is in essence having to look at all n characters. And there's n divided by 2 diamonds. So the substring is looking at n squared divided by 2. It's even worse if you think about how many characters. So we say that, as you can see, as the size of the string gets big, then n squared gets really big. So in fact, it slows down, and Dr. Planck coded it up again. So with just 10 diamonds, it's fast. With 100 diamonds, it's fast. With 1,000 diamonds, still fast. 10,000 diamonds, we're starting to slow down a lot by 80 times now. 100,000 diamonds, and now it is almost 80 seconds. And in fact, 10,000 to 100,000 is an increase of 10. 10 squared, remember, we're looking at n squared. So 100,000 squared is 100 times greater than 10,000 squared, and sure enough, it runs 100 times slower. So for really big diamonds, when we hit the mother lode, it takes us a while to mine it. So we have to ask ourselves, is there a better way? Can we do better than n squared? And the answer is yes. We can use a list in a clever way to do it in what we call linear time. So let's take a look at how we can do it in a more clever way. What we're going to do is we're going to read the string into a list. So each character is going to be made into a list node. So we read all of the characters in the mine or the string, and one by one we put them into a list. And now what we're going to do is we're going to iterate through the list using 2 iterators, left and right. And anytime left is a left or less than sign and right points to a greater than sign, we must have a diamond. Right? Does that make sense? So when we find a diamond, we're going to increment the number of diamonds by 1, and we're going to reset left so that it points to the item to the left, which is this item right here. So Dr. Planck actually saves, creates a third iterator called new left. So new left is made to point to the character or node to the left of left. Now we delete what left and right point to, so you can see they're gone. Okay, so these two are gone from the list. And now we set left to be equal to new left. And we advance right so that it is one to the right of left. Okay, so we do that again, and we see that we have another diamond. Because left is a less than, right is a greater than, so we increment the number of diamonds to 2. But now we have a different issue, a boundary condition. Remember the last test, boundary conditions? What is to the left of left? The sentinel node, the big X. So there's really nothing to the left of left. So in this special case where we were at the beginning of the list, the boundary case, we have to set new left to actually point to the right of right. So this is a boundary case. Those boundary cases kill you if you're not careful. Okay, we can't set left to be the sentinel node. So in this case, left will be reset to point to here. So when we delete left and right, left now points to here. So now you can see right is no good. It's a right arrow. So we advance left to be here, and we advance right to be here. So in the next frame, left points to here and right points to here, and we have a diamond. So again, we delete it. And now you can see when we advance right, right ends up pointing to the sentinel node, so we're done. Because obviously with right pointing to the sentinel node, there can be no diamonds left. Okay? Now, you might be asking yourself, why do we have to complicate things by having new left? Why don't we just delete left and right, and then set left to be left minus minus? Let's just delete left and right. Okay, so they're gone. And when we then say left minus minus, well, I told you, decrementing an iterator will make it point to the previous item, so why can't I say left minus minus? Because what? No, that's not the problem. To the left of left is this item. If I delete left and right here, there's still one item. Yes, John? Nope, that's not the issue either. I delete left and right, and then I decrement left. Pardon? Nope. If I say left minus minus, minus minus does take you to the previous element. Bingo! Very good. Give this man, if I was Dr. Plank, I'd have candy, and you get candy at this point. But I don't. Too early in the morning. Actually, that's when you need candy, that sugar hot. So the issue is that left and right have been deleted. So left minus minus, possible seg fault. It's no longer around. You can't do anything to something after you delete it. So we have to save left minus minus. So before we delete left, we have to save it in new left. That's what happened. Don't fall into this trap. This is a pointer trap. Once something is deleted, you can't use it anymore. You can get seg faults or other bad stuff happens when you try to use something you've deleted. So you have to save the value if you want to reuse it. Okay, so this code isn't going to look nearly as nice. Let's take a look at it. Yes? Oh, it's horrible if it's a vector. Because it's a contiguous memory block. When you delete the two items, now you have to bring everything that's to the right of it, you have to smush together it automatically smushes by moving them. Right. So it would move every single one. It would move, when you erase these two, first you do erase on left. So it would first move everything to the right of left, one item to the left. Then you would delete right, and it would do it again. It would move one item. So it's not even smart enough to move two items. You'd say delete left, and to close it up, it would have to move every item to the right of it, one item to the left. Then you would say delete right, and again, it would move every element to the right, one element to the left. So it would be really bad. You really don't want to use a vector here.
Well, I guess what I'm thinking is, you do the minus minus, even though you delete it, doesn't the pointer still keep the new address?
It does. So now you could, yes, you could use some fancy footwork to try to do this. So I don't want to go into it. You could use some fancy, but you can't use the erase command. You could do some other fancy footwork to make it work with a vector.
The list stores the next pointer inside the data structure, and you delete that. That would be the reason why you can't minus minus after delete.
Yes. Well, after delete, it's gone. Yes, you've lost the node. The node, yes. The node, you've lost the pointers. The node that pointed back and forward is gone. That's why, yes. Now, yes, with clever, if I was cruel, I'd say figure out how to do this with a vector and not using erase. But I won't. Okay, other questions before I move ahead? Okay, so let's look at the code. It's not nearly as nice. So look at the code for, first of all, this was how long it took with find. Very nice and pretty. I can't even fit the code for the list onto one screen. So it's not nearly as pretty, but it's a lot faster. We prefer speed. We will prefer a bigger program that runs a lot faster. So what do? Well, our list is storing chars. Every node stores one character from the mine. So the first thing we do is we just go through the mine. Remember, we can treat a string like a vector. And we push back the character onto the list. So we're just treating the string like a vector here. So we set our number of diamonds to 0. Left is set to L.begin. And in this case, we're saying while left is not equal to L.end, we first check to see whether left is equal to a right arrow. If it's equal to a right arrow or a greater than sign, it can't be the start of a diamond. So we increment left, and we'll come out of the loop. So if left is not the beginning of a diamond, move on by incrementing left. Else, we set right equal left, and we increment right so that it points to the next element. If right is pointing to the end of the list, we return. Again, there can be no diamond. Otherwise, if right is pointing also to a left arrow, it cannot be the beginning of a diamond, so we move on by incrementing left. Otherwise, right must be pointing to a right arrow or to the greater than, and we have a diamond, so we increment the number of diamonds by 1. We also need to do some other stuff, which is we need to do adjustments to left. So we need to find out whether we are at the beginning of the list or not. If we are at the beginning of the list, the first item of the list, then, as I showed you earlier, we set new left to right and then increment new left by 1. Otherwise, we set new left to left, and we decrement new left. And I thought, when I read this, why not just say right plus 1 and left minus 1? It's because lists don't support the minus or plus operations. So you have to say minus minus. So this first one handles the boundary case where left is at the beginning of the list. The else handles all other cases where we're not at the beginning of the list. Once we have got new left, we can erase left and right and set left to be new left. So it's a lot more complicated, the code. And this is why you should draw pictures first, okay? One of my biggest challenges with many of you is getting you to draw pictures when you are trying to figure out how to write a program. Generally, you write a picture, or if you draw a picture and you play with the picture, you'll figure out how to write the program. But if you just start trying to write the program, it's often a lot harder. So I strongly encourage you, as the problems get more complicated, to try to solve things by hand first. Draw some pictures, work out a couple small examples using the pictures, find the boundary cases, and again, work things out using pictures, and then write your code. I cannot overemphasize the importance of using pictures to solve things. Okay, even if you think verbally, believe me, pictures can help. Okay, so my claim is this is a lot faster. Okay, and the reason it's a lot faster is that we only move through the list once. Okay, we're not moving through it n times like we did with the previous find. And every time we do a delete, we only move left either to the left one element, or we move it to the right and affect one element. So we're not doing n divided by 2 moves every time like we were, or n moves actually, with the find. So this is actually for n items, or n characters in the string, we are looking at roughly n items. So if we have 100,000 diamonds or 100,000 characters, roughly speaking, we only look at 100,000, not 100,000 squared. So again, Dr. Planck coded it up and he ran it. And with 1,000,000, it took half a second. With the find, that beautiful, elegant find, it took us a mere 80 seconds. In other words, 160 times slower than with the list implementation. So yes, the list implementation was longer and not as elegant, but it was sure as heck a whole lot faster. What we say it ran in n time rather than n squared time. Remember, one of the big things about this course, getting you to code more efficiently. So just because you find a cute solution, and I will admit this is a cute solution, it is not a very good solution in terms of running time. It is a very slow solution. So just don't always code up the first thing that comes to mind. You also need to think about, especially when it's n squared, is there a better solution? So in this course, we're also trying to get you to think about, is there a better way? Okay? So questions about that? Okay, a segue. Actually, back to something Dr. Planck covered in a previous lecture, but I didn't think it was the right time to cover it then. So in the middle of his pointers, he introduced sorting using the STL, and I thought it was a bit of a non sequitur because I didn't think you were in a position yet to understand how to sort a vector, but now you are because we've introduced the notion of iterators. So you can sort a vector using the sort method. And in order to do that, you have to include a library called the algorithm library. And it can sometimes, you want to sort things like you might read in. Remember I said that I could sort a list? So earlier in this class, I sorted a list, but I did it really inefficiently. The way I sorted the list was horrible. Okay? So a much faster way to sort that list would actually have been to read it into a vector using pushback and adding everything to the back of the vector. And then C++ has this sort function that you can get from the algorithm library. And you give it where you want it to start the sort in the vector and where you want it to end the sort. So these are both iterators. In this case, lines.begin says start at the first item. Lines.end says that's the Sentinel node, so it's saying sort the entire vector. And it's a much more efficient sort than the one I just showed you. It uses something called quicksort, which you'll learn about in 302. Not going to show it to you in this class. Okay? But sorting is a rather common operation, and sort is best done on a vector because it's contiguous in memory. You can also sort the items of a list. If I changed from a vector to a list, the sort algorithm should also, I think, I didn't try it, but should be able to sort the list, but it would be a lot slower. Turns out that sorting with contiguous memory is a lot faster than sorting in what we call non-contiguous memory, and lists are non-contiguous memory. So just tuck this away. I don't think you have to use the sort function in this course, but I wanted to show it to you because it was in Dr. Plank's notes. Okay. Now, I know we've covered a lot. So we've covered lists. Today we covered Deques. But there is one other thing I do want to show you because you're going to start to see it, and it's unavoidable. And that is reference variables. So, got about 10 minutes. I am going to go through the part of the notes that he said he didn't lecture on because there is something important here. So, just like you can have 2D vectors, you can have 2D lists. So I could create a list and each value in the list is itself a list. Okay, and this actually happens a fair amount where you want each list item to point to a list. So let's say this was our Facebook server, and the first one, the top level list, was members. And then this value is our friends. Okay, so we kind of need a list of lists. The top level list being our members, and then each member having a list of friends. Okay, so he does it by having his list of lists is simply going to contain 10 numbers each. So his list of lists, the first list has 1, 2, 3, up to 10. His second list has the numbers 11, 12, 13, up to 20. His last list has 91 up to 100. So he has 10 lists. Each list is a list of 10 numbers. So he has his type def, which he loves. He creates an int list, which is a list of int. And now this is what he's saying is important. Every list should actually be a pointer. The value should be a pointer. I'm sorry, each list should contain a list. Yes, I'm right. Each list should contain a pointer to an int list. So our list is actually going to be 10 pointers. So each list item is a pointer to another list. Okay? And he goes through his, from j equals 0, j plus equal to 10. So as I said, he's putting 0 through 9 on the first list, 10 through 19 on the second list, so slightly different than what I said. So each time he creates a new int list, he pushes that new int list onto his first list, and then he runs through that new list and puts 10 numbers onto it. Okay? And it all works out quite nicely. Now, many of you aren't comfortable with pointers. You don't want to do it this way. Okay? Because you don't like all these arrows. The compiler's always complaining at you because you used a dot and it wants an arrow, so now you changed it to an arrow. And it seems that now that's not right. The compiler wants a dot. So you say, phooey on pointers. I'm not going to use pointers. I hate pointers. Okay? So I'm just going to use a list, and I'm not going to worry about those silly pointers. I'm just going to make every list be itself, the value is going to be a list. So effectively, instead of pointing to a list, what I'm going to have is each list item is going to be enormous, because each list item is going to actually store its own list, like this. So instead of pointing to a list, each list node contains its own list. And you're happy, life is good, because there's no pointers. So we are creating an int list, and that's going to hold our list of 10 items. And we push back our int list. Hello? Sorry. If I can hear you, other people can hear you. So please keep it down. So we push a new list onto our list. And then we add 10 items to IL. And it seems like we are good. So things should be good. We print it out, and it's a mess. The first list has 0 to 9 on it. The second list has 0 to 19. That's not what we wanted. What we wanted was the first list to have 0 to 9, the second list 10 to 19. We don't want the second list to have 0 to 9 on it, nor should the third list have 0 to 9. The problem is that we never cleared IL here. So by not clearing IL, it doesn't work. But another problem is that IL is not the list we created. So IL is sitting out here by itself. Here's IL. It's its own list. So when you add things to IL, you are not adding them to, so like when you add 10, 11, 12, 13, you're really not adding anything to this list. You're actually adding it to IL. So that's no good. Okay? In fact, what you did not see is that the very first thing here was a blank line. Because your very first list, when IL started, IL was empty. We pushed 0 to 9 onto IL, but nothing got pushed onto this list right here. So then when we pushed IL onto the second list, we got 0 to 9 on this list right here. This list actually had, this list right here had 0 to 9 on it. It wasn't actually the first list that had 0 to 9. So it's all messed up. You're thinking, uh-oh, maybe I did need to use a pointer. But then you get smart. And you think, okay, rather than using IL, I will simply resize the list first to add a new one, and then I will do this yucky numslist.back that gets me the list, I just created and push back onto that. Okay? And it works, but it's yucky. So, I get to my final point for today, which is you have not yet seen reference variables used in outside of reference parameters, but you will start seeing them in the book. And you need to be aware that you can use a reference variable outside of an argument list. And what I have done here is I resize my list to be size plus 1, and then I get what's called a reference to the last list. And this is a constant. I can't change it ever. It's like a pointer, but it's not really a pointer. It's just a reference to the last item of the list. And now I can call pushback using this reference variable. So I can get away with not using pointers if I use reference variables instead. Okay? So a reference variable is a constant. It has to be given a value when it is declared, and it can never be assigned a new value. It points to some item, and it allows us to get away with not using pointers. Except it really doesn't, because it's just another form of a pointer. I do not expect you to know how to use reference variables in this manner in this course. I only expect you to be able to use reference parameters. But the book is going to start using these reference variables sometimes, and you need to at least know how to read them. Okay, so I would encourage you to go through, and while I'm not going to hold you responsible for reference variables, I would suggest you at least look at this because you will start seeing them. Okay, on Thursday, we'll start into our next data structures, which are sets and maps. And we're also going to have your introduction to looking at something called Big O, which is how we formally analyze the running time of a program.